Yeah, so question four, when we were doing these intermolecular forces, right, I made the joke that no one laughed at, that this is the intermolecular force that's literally holding your life together. Right, hydrogen bonding is the key intermolecular force in DNA for question four. Right, and we talked about between adenine and thymine, there's two hydrogen bonds, and cytosine to guanine, right, there's three hydrogen bonds, but it's that hydrogen bonding pattern that's important in the recognition for those pairs. So yeah, that would be an example of our hydrogen bonding for question four. All right, so choice C. Question five, we're given these two isomers of each other, right? Diisopropyl ether, 4-methylpentanol, and we're asked to rationalize why one might have a higher boiling point than the other. And there's two ways to figure out, there's two arguments we can make about boiling point. One is, in general, larger molecules are going to have a higher boiling point because they've got more intermolecular forces. We can't use that argument here because both molecules are isomers of each other. They have the same formula, the same number of carbons, hydrogens, and oxygens. So we can't use the one's bigger than the other. They're going to have a different boiling point. So the argument we're going to have to make is a difference in intermolecular forces. And if we look, this diisopropyl ether, we have an oxygen, but it's within this alkyl chain. So yeah, we've got a carbon-oxygen bond, so it's going to be slightly polar. And because we're polar, we're going to have, some dipole-dipole, but not really a lot of dipole-dipole forces. Whereas if we look over here, right, I've got an oxygen connected to a hydrogen, right? We have the strongest intermolecular force possible. We have hydrogen bonding. So because I have that hydroxyl group, that OH, I have the potential for hydrogen bonding. That should have the strongest intermolecular force of those listed. So, because they have identical formulas, no, they can have different boiling points. Diisopropyl ether, no London dispersion forces, not stronger. Dipole-dipole, it has dipole-dipole, but they're not the strongest. And then the alcohol, right, has a higher boiling point because it has hydrogen bonding interactions. So we're going to make an argument based on intermolecular forces because there's a difference. Is there a difference between saying there is more branching versus it's a larger molecule in terms of boiling point? That's a different question, right? That was the question you had in the group me. Right. So just a quick aside about that question. Right, we did this in class where we looked at isomers of pentane. So like CH3, CH2, CH2. Maybe it was isomers of butane, but whatever. This will also work. And then so this is your question about branching here, right? All of these have the same number of carbons, same number of hydrogens. And so we can't say one is larger than the other. They have the same molecular weight, right? They have the same number of carbons and hydrogens. So here it's like how they fit together and the surface area for the intermolecular forces. And so we have this nice long chain here, right? That larger chain, more surface area for overlap, higher the boiling point because we're going to have more London dispersion forces. Whereas I kind of in the group me, I use that Tetris analogy, right? It's really easy to fit that long, thin piece in Tetris, whereas the weird shaped pieces in Tetris, right, they're harder to put together. And that's what we have down here with this neopentane. harder to fit together. Right, lower surface area, we're going to have lower London dispersion forces and a lower boiling point. So it's a little bit different than the question on the practice exam, because in the practice exam, it was an argument of stronger intermolecular forces. Here, all the intermolecular forces are the same. It has to do with the shape of the molecule and how those molecules fit together. So that's a good thing to look out for, right? Is there a difference in intermolecular forces? Yes or no? Here, there is a difference. I've got hydrogen bonding versus dipole-dipole. That's going to be our argument. But if these were both, if these both had alcohols, then they probably would have very close to about the same boiling point. Question 6. Oh, yeah. Question 6. I wish this all was on one page. The correct intermolecular forces, right? Methane is nonpolar, so it's just going to have London dispersion forces. Oops, I just inserted that page. All right, water, hopefully we all know water is going to have hydrogen bonding. Potassium chloride, and it's aqueous, so it's going to be in water. So we can have something that is ionic. So that's going to be ion dipole. And then here I've got a carbon fluorine bond. We know fluorine is the most electronegative, so that's going to be a polar bond. So we're going to have the opportunity to have dipole-dipole intermolecular forces as our strongest intermolecular force in question 6. Yeah, question 7 came up in office hours as well on Friday, right? Match the normal boiling point to each of these substances. Again, we're just kind of thinking about intermolecular forces here because we know stronger intermolecular forces, the more energy is going to be needed to separate that liquid into the gas phase. So stronger intermolecular forces, higher the boiling point, right? The more energy we have to put in to take this sample from the liquid into the gas phase. So we know, we just talked about methane in the previous question, right? We said methane has London dispersion forces, weakest force present. We know here I've got hydrogen bonding, and we know down here we have hydrogen bonding as well. And then here we're just polar, so we're going to have dipole, dipole. So, okay, weakest intermolecular force, the lowest boiling point. I did put a trick in there. I guess we can cancel out a few of these. Right. Maybe that's what made it a little bit harder, is that we can cancel out minus 273 because that's absolute zero. We don't have a boiling point at absolute zero for anything here. From there, it's kind of a process of elimination of, and then there's one more. We can have 1275. Nothing has a boiling point that high. So for the rest of these, it's kind of like process of elimination of, okay, methane, London dispersion forces, weakest intermolecular force. That probably has a boiling point of minus 162 degrees Celsius. Next, the next weakest intermolecular force, right? The hydrogen sulfide. So that's going to be minus 59.6. And then we're left with these two, 64 and 280. So methanol, I've got hydrogen bonding. Here I've got 1, 2, 3, 4, 5. Pentanol, we also have hydrogen bonding, but because pentanol has a longer chain, it's going to have more London dispersion forces, higher molecular weight. Both of those things raise the boiling point. So methanol would be next at 64.6, and then the pentanol would be the highest at 280 degrees Celsius. So that's, yeah, I kind of added, 2 extra ones in there to kind of, throw you off a little bit, but basically all we're doing is looking at intermolecular forces. Stronger intermolecular forces, higher the boiling point for those compounds, throwing out the outliers there. Question 8, rank the following hydrocarbons in order of increasing boiling points. Oops, not what I wanted to do. So yeah, this is similar to the question that was asked earlier about the impact that branching has on boiling point, right? So we're asked to order them in order of increasing boiling point. So we want to go from low to high. So the lowest boiling point, right? More branching, lower the boiling point. So B should have the lowest boiling point, followed by C, right? And then A should have the highest boiling point because it's just a straight chain, right? It's going to have the most surface area. Right, so we kind of got to that discussion a little bit earlier because that question came up earlier. So yeah, B, the most branching, has the lowest boiling point. C just has one branch off of that chain, so it's going to be next. And then A is going to have the highest boiling point, right? Because it's this nice long chain alkane. It's going to fit together nicely, maximize surface area, maximize our LDFs, have a higher boiling point. All right, I'll take the first break there because that was question 4, 5, 6, 7, and 8. And then we'll start up with question 10.